Hello, hi, hope it's going well. The next stage in creating our system is we want to be able to pass in uniform data. Otherwise, we're not going to be able to do much. To start with, let's declare a struct which will hold a bunch of data for a uniform buffer. Okay, so we're setting things up for a model view projection stack. If you are not aware of what that is, well, I applaud your ambition in jumping ahead. But if you're not aware of what this is, I do have a video on the basic concept if you check out my fundamental computer graphics concepts. Okay, so the next part is we want to use that model view projection data in our vertex shader, so we will declare that. Okay, then we can go ahead and apply the transformation stack. So remember, it goes matrix multiplication goes in opposite order, which is why it's declared this way. Or rather that way. Okay, cool. So the shade is looking good. What we'll then have to do is recompile it. So we pop over to our shaders folder, and before I was using a shell, but we really can just double click and then just check the modify date. It matches up to right now, so that's good. That means there weren't any errors. The reason I typically run it within a shell is because if there are errors, it pauses before exiting. I can see the errors. But okay, so we've got that in. We'll then need to create a what's called a descriptor set layout. So this is to do with the graphics pipeline. So we'll jump over to the graphics pipeline section. We'll make a function to create this. Okay, just a bit of programming bureaucracy here, defining a few things, how this is going to be used, where it's going to be used, and so on. Next, we'll actually create the thing, and in order to do that, we will need to declare a member variable for it. It doesn't really matter where we put it, let's put it here. Okay, cool. So that is the function which will create a descriptor set layout, and that is called pretty much where it is here. So after render pass and before graphics pipeline. Okay. So once we've created the descriptor set layout, we will need to incorporate that into our graphics pipeline, which is why it was called at that point. Now if we go back into here, right down the bottom, maybe not that far down. Okay, pipeline layout info. So if we check this, there was another bit here with the stuff with set layout count. We can set that to declare our descriptor set. Okay, cool. So now we will, gee, that's a big function. When I was studying C at uni, we were penalized if our functions went above 50 lines. We had to, split it up. But hey, real code, it's big. All right, so now we're going to create uniform buffer. Now, a uniform buffer is passed in at every frame, and it updates every frame as well. So it would be one thing if we had a uniform buffer which didn't update, then every single frame could access it just fine. But because we are updating things, we don't want to mess around with like race conditions and synchronization and things like that. So the long story short is we can just simply create a uniform buffer for every single image on our swap chain, which shouldn't be too much work. I mean, shouldn't be too much memory requirement because we're only storing matrices. It's not like images. I mean, they take a lot of space. So here's what we're going to do. We'll create a vector. Yeah, that should be fine. Okay, so just like the vertex buffer, we had a function to create that. We will also make a function to create our uniform buffers. Okay, cool. So again, nothing too crazy. We iterate through all of the uniform buffers that we are going to create, and we specify we're going to be using the buffer as a uniform buffer. That should make sense. We want it to be host visible so the CPU can write directly to it with memcopy, and we want it to be host coherent so it synchronizes properly with the multi-threading and stuff. The data appears the moment we write it, that sort of stuff. Now, there's no real benefit to using a staging buffer because, well, as you know, a staging buffer involves creating an extra buffer to do a memory transfer, and you do get it into high performance memory. However, there is an overhead in creating and destroying a temporary buffer. So that's useful when we're passing in data once and then reusing it. However, for something that we're dynamically updating, this is probably the better way to do it. Okay, now because these uniform buffers are bound to the swap chain, the number of images on the swap chain, it's probably good practice to destroy and recreate them every time the swap chain is destroyed and recreated. So we'll create some stuff here to destroy the uniform buffers. There we have it. And while we're at it, we should also call the function to create that stuff in the first place. So if we go to the Vulkan initialization, we should probably do that around the time that we create the vertex buffer. Okay, so that's all well and good. The next step is we will create a function which will update that data every frame. Will be called every frame to update the data. We want to start doing some cool stuff, so in order to do that we're going to bring in a few extra pieces. Okay, so we want to work in radians. I think by default GLM works in radians anyway, but we can specify that we're forcing it to work in radians. We want to use matrix transforms, and I want this to update every frame, so I want to kind of use timing as well. So we can include the chrono library, which has basically just high precision timing functions. Okay, and because this is happening every frame, why not? We'll define it here. So what this is basically doing is taking the time difference and getting that in seconds. A little bit complicated, I know, but this is one way to do it. We might be thinking, okay, well, if we call the time right now and then the time right now again, won't the time difference be 0? Well, the difference is this static sets start time up as a global variable, and this line is only called once, the first time this function is called, and then it's not updated after that. Our next task will be to create a uniform buffer object structure, populate its matrix transforms, and then copy it into the uniform buffer memory corresponding to the current image index. Okay, so what we will be doing to the object is just rotating it around the Z axis. The first argument here is the matrix that we want to multiply this transformation onto. So typically if we had a whole bunch of transformations, when we stick on another one, we would put the reference to the object that came before, if that makes sense. But if we're making one from scratch, then we multiply it onto the identity, which has the result of just returning the new transformation. So the way we make the identity is we call matrix 4, pass in a 1, and by default it puts the 1 on the leading diagonal and zeros everywhere else, and it makes an identity matrix. The other thing here is this third argument is the axis around which to rotate. We just want to rotate around the Z axis, so we'll put that in there. Cool, then we create the view. Okay, so we use the look at matrix thing. First argument is the position that we are looking from. Second argument is the position we're looking towards. So our triangle will pretty much be at the origin and we'll be looking at it from some distance off. The third argument is the basically the up direction, which is just up in the Z axis. Now technically, if we are at a point and we're looking down, then our local up direction is tilted a little bit. However, for this simple example, it works just fine to declare it this way. Okay, so then we create the perspective projection. This first argument is the field of view angle. So if we go 45 degrees each way, this is a 90-degree field of view. It's something. The next argument is the aspect ratio. And the last two arguments are the near and far distances for clipping. There's another thing to note, and that is that OpenGL and Vulkan use different conventions when it comes to their coordinate systems. For OpenGL, y positive is upwards on the screen, and for Vulkan, y negative is upwards on the screen. For that reason, we need to adjust the projection matrix. I'll just write this in. So the way we do that is we go okay, cool. So then our task is to copy the memory over to the current uniform buffer. Okay, cool. So that is defined. Now, of course, we need to use this. So we'll go to the draw frame, and at this stage, pretty much we've got the image, we're ready to go. So we'll call update uniform buffer on our image index. And let me just see if there's anything else I forgot. Ah, yes, okay. So, of course, when we clean up the swap chain, we destroy the our uniform buffers, so we will need to create them again when we recreate the swap chain. Recreate swap chain. Okay, cool. So that's all well and good, but we need to bind that information in, basically, to the graphics pipeline. This next part's going to be a bit of a slog, because it's really just dotting our I's and crossing our T's, but the basic idea is we have something called a descriptor pool, and the descriptor pool has descriptor sets allocated to it, and then descriptor sets are bound to the pipeline. It's going to be a little bit, because really it's going to be the same, a copy of the same descriptor set for every single swap chain image. But let's just get in and get it done. Okay, so we have a descriptor pool and descriptor sets vector that will be populated by some functions. So I'm just going to go down. Where should we put these? Well, I guess since we have descriptor set layout here, let's create our functions here. Okay, cool. So again, descriptor pools, pretty simple because they don't do much. We just need to declare that we are creating that we are allocating uniform buffers to this pool, and we specify the number of, basically the number of uniform buffers that we're going to allocate to the pool. That actually matches for both of these. Right, then we go ahead and create that. So then the next question is, where is this created? Well, this is again bound to the swap chain. So first of all, we create and destroy, well, we create it in the Vulkan initializer. Just after the uniform buffers, I guess. And because this is bound to the swap chain, then it will have to be destroyed in the cleanup swap chain section and then created again in the recreate swap chain. Apologies for all the rapid scrolling, but let's find, yep, recreate swap chain. After the uniform buffers, we'll do this again. And then down here. Okay, cool. So what will we do now? So pretty much we have got our descriptor pool. We will need to create descriptor sets and allocate them to the pool. Now, this is the big one. This is a slog, and there's not a lot of payoff, but we do have to do it. Okay, so what we've done now is we've allocated descriptor sets. So again, remember this descriptor sets here is the member variable that we declared up above. We allocate each descriptor set to the descriptor pool, and yes, they are all the same. That's fine. Things like this up above, when we create our set of layouts, that has to have the same number of elements as the number of descriptor sets that we're going to allocate. However, they are all going to use the same layout, so we just, we create copies. It's fine. It is what it is. So the next step is we need to basically write the buffer information to each of the descriptor sets. Okay, cool. So the descriptor sets were allocated to the descriptor pool. Then we declare here that we are going to pass in our specific uniform buffer. This is the actual data that we're going to pass in. Offset and range, the amount, you know what I mean, the size of data that we're passing in. Then we describe a write operation, a destination set, so we are writing this uniform buffer to our descriptor set on binding 0, array element 0, that's fine. We're writing a uniform buffer, and yeah, okay, it's a lot of writing, a lot of typing, but there it is. So then the question is, where does this occur? And basically it occurs every time we create a descriptor pool. So if we go to the Vulkan initialization, descriptor pool, then we will create our descriptor sets. And same thing in the recreation. However, we do not have to clean it up. Because the descriptor sets have been allocated to the descriptor pool, they are within its control, and the descriptor pool will destroy all of the descriptor sets when it itself is destroyed. Okay, so we're almost there. We need to go down to the graphics, the create command buffers. So remember, a command buffer records the operations involved in a draw of a frame. So what do? We bind the vertex buffer, that's fine. Then we go to draw, but before we draw, we need to grab the descriptor that will be used in the draw. Okay, so there are a few arguments involved here, so I'll step through them. The first few should make sense. Then if you look here, the next argument we're expecting is the first set. There's only one, so we'll go with set 0. Descriptor set count is 1. Descriptor sets, so that is that one there. Dynamic offset count, none of those. And pointed to dynamic offsets, again, we don't have any, so we'll just go null pointer. So that should be working, fingers crossed. If we go to run this, okay, we're getting nothing. However, if we look over on the validation layers, we also aren't getting any errors, so that's good. We can get this working if we go to the graphics pipeline, and what it is, it's the backface culling. So down to the rasterizer, and we're just going to reverse that counterclockwise. And then again, fingers crossed. And there it is. Whoa, that's mad. All right, so that'll be it for today. Pretty big video, but cool result. And yeah, cool. Okay, so I'll see you next time. Bye.